Okay, it lets you look at these special graphs, these special functions. Would you care to turn the light out so maybe that these can be seen? These are entitled functions, so it must mean that all of these particular graphs would pass the vertical line test and they would be functions. This is an example of a linear function, of which in this chapter we're going to graph a lot of them. We're going to write equations for a lot of them. Really, that's what the whole chapter is about. The rest of these graphs you see are not linear. They're different types of curves, all different types of curves. You will hear these referred to as the parent graphs. For example, this one looks weird, doesn't it? It's called the step function. You can kind of see how it looks like stair steps that you would go up. Different and kind of unusual is that it has an open circle and then a closed circle, an open circle and a closed circle. That open circle means that that particular part of the graph is not, or that particular point is not part of the graph. So if I drew a vertical line down through there, I would hit an open circle, which is not a point, and a closed circle, which was. And so that's why that's able to pass the vertical line test, and we call that the step function. I would make little sketches of these real quick. We talked a little bit yesterday about this V-shaped graph, and we called it the absolute value function. And I said it's kind of easy to remember because you can even hear that sound, in, an absolute value to know that there is a V, and that's a V shape. If I do the vertical line test on this graph, of course, I can only hit 1 point because we said as the graph goes up, it also goes out, and it never does get straight up vertical, and so it passes the vertical line test. This is a quadratic function. Does anybody remember the P word, what you call this graph? Yeah, that's the way it's spelled. But it's a parabola. Spelled parabola, yeah. But it does pass the vertical line test, and it is a function. This next part, I always call this a S-curve. No matter where I go through that graph, I can only hit 1 point. So, draw vertical lines in there. It is called a cubic function, and the reason is because this is y equal x to the third, or x cubed. And so anytime you have an x to the third, that's what that looks like. And then this is the square root function. Just start down there really at the origin. It kind of looks a little messed up. But if I did the vertical line test on there, still, even though it's not linear, it still passes the vertical line test, and it's still a function. And then this one is an exponential curve. What it does is it approaches the x-axis. Whoops. It's hard to do with this little stylus here. And then it goes to infinity. Now, it never does really just get horizontal here, because theoretically speaking, it gets closer and closer down here to the x-axis as you go. But anyway, it does pass the vertical line test, and it is an exponential function, an exponential graph. So all those are different types of functions, and we discussed yesterday lines, mostly. We talked about a circle. A circle was not a function, right? What kind of slope do you know that this line has? Positive or negative? Since it's increasing from left to right, it's got a positive slope. And of course, it is a function. It passes the vertical line test. What was the only kind of line I said yesterday that does not ever pass the vertical line test and is therefore not a function? Yeah, vertical line is the only type of line that's not a function. So I'm looking at all those are functions. If I real quickly here just did a sketch of a sideways parabola, is it a function? No, it is not. It does not pass the vertical line test. We did a circle that didn't pass the vertical line test. A vertical line does not pass the vertical line test. What if I had a graph? You'll have to excuse the sketch there. But what if I had a graph of just a curve like this? Does that pass the vertical line test? No. I hit 1, 2, 3, 4, 5 points already on that curve. So that's not a function either. So you use a vertical line test to determine whether a graph is a function. Any questions so far on any of those? On those, yeah. That's all we were doing. So that just gives you some example of what is and what isn't. Alright, we're going to talk about those again a little bit later. Alright, let's look at this equation right here. 3x minus 2y is equal to 12. Does anybody know what form that equation is written in? It's a linear equation. It's got an x and a y, and they are both to the first power. And neither one of those x and y are in the denominator, not multiplied together, not under a square root symbol, absolute value sign. Does anybody remember standard form? Anybody remember talking about standard form and doing graphs of lines? So in this particular case, A is 3, B is -2, and C is 12. So this equation is a linear equation in standard form. All right, this says complete each ordered pair so that it is a solution to this equation. All right, we're going to work some problems like this together so that you can do some on your own. We're going to take A, for example, first. And what comes first, X or Y in an ordered pair? Very good. What's the special name for the X? Starts with an A. It's a weird word. Abscissa. Good. What's the special name for the Y? Ordinate. What is a relation? A set of ordered pairs. What are the 5 ways to represent a relation? Set, graph, mapping, table, equation. Very good. And we've already discussed today what a function is several times, so maybe you've got that somewhere in your head. But if this is X and we're looking for Y, then that means I'm going to take 2 and plug it in the place for X. So here's what we'll do. This is what you'll write down. I just put the 2 in the place of the X. Now that's good because if I have one equation, I can only solve for one variable at a time, not 2. Chapter 7, it'll take 2 equations to solve for 2 variables, okay? All right, so what's 3 times 2? All right, so we're going to solve for Y. What should I get rid of first? The 6. So I will subtract 6. The sign in front of the number goes with the number. That is positive. And so we will subtract 6 from both sides. Divide both sides by -2. And Y is -3. So that means that this solution, this ordered pair, is 2, -3. What does that mean? Not only is that a solution to this equation, but if we graph this line, this linear equation, graph this line, the point 2, -3 would be on it. Okay? All right, let's do the next one. If I'm trying to squeeze this up a little. All right, next we're going to try -2, again, in the place of X. So we'll have 3 times -2 minus 2y is equal to 12. Three times -2 is -6. And then this is a simple equation we could solve in chapter 3. I've got minus or a negative 6 in the way. So to undo that, we'll add 6 to both sides. 12 plus 6 is 18. Divide both sides by negative 2. Y is negative 9. So this would be negative 2, negative 9. So I've got 2, negative 3, which is a point on my line, a solution to this equation, and also negative 2, negative 9. Any questions about how we're doing that? Is that pretty easy? Solving equations?
So, no. Just see which one out. That was like.
We're looking to see what ordered pair, like on a graph, like 2 what would be on this line? Well, 2, negative 3 would be. So let's say this is 2, this is a rough sketch here. Here's 2, negative 3. And then here's negative 2, and somewhere down here is negative 9, and that's another point on this graph. Until all of our points will be in a straight line. They will be points on the line, they will also be solutions to the equation. That's a good question.
So, like, once we get it, after we get our answer and then graph it, we'll be able to tell whether it's a solution or a function or not a function?
We could, but I will tell you this. This is not a vertical line. You can already tell right now, right?
Mm-hmm.
So is it a function?
Yes.
Yeah. Because the only type of line, remember, that's not a function is a vertical line. So here's the point of all this, though, really. It's not really to tell if it's a function, because we already know if it's not vertical, it is. The point of this is to show you that these ordered pairs are solutions to this equation, and the graph is just a picture of that. And if I took all the solutions to that equation and graphed them, I'd get the line itself. A line is just a picture of all the solutions. What is a line? It's just point. I mean, infinitely many. It's just a collection of points. Every place on that line is an ordered pair that is a solution to this equation. All right, so let's look at the next one. How is the next problem a little different? Instead of giving me x, they gave me y. So in the place of y, we'll put a 3. All right, would you solve for x? Work a little ahead of me there and see if you can do that.
How did you get the first of the egg?
It's for the y, and it's right here. See, it's in the y spot, and so I took it right up here and put it in the place of y. We can, yes, and the point of that is that those ordered pairs on the graph are just a picture of all the solutions to this equation. All right, so what hopefully you've done first is you multiply these two numbers together, right? Very good. What did you do next?
Add the 6.
Add the 6. Good. And then you what?
You divide it by 3.
You divide by 3. What's your answer? So if x equals 6, what is your solution? Come back up here. 6, 3. That is another solution. So we have 2, negative 3. Whoops. We have 2, negative 3. We had negative 2, negative 9. Now we've got one more to do. All right, plug negative 6 in for y and solve. So in the place of y, we're going to put a negative 6. Do this on your paper too. Do this ahead of me. Work that problem out. Move that pencil a little bit. Get involved. What is negative 2 times negative 6?
112.
Here's one of those problems where everybody will say, oh, there's a 0. This must be no solution, right? That's not true. 0 is a number 2, isn't it? So if I subtract 12 from both sides, And then, good, and then I divide by 3. What is x? 0. So 0, negative 6 is a solution. All right, let me ask you a question. What quadrant is 2, negative 3 in? Go over and down. Fourth. Fourth is right. All right, what about negative 2, negative 9? What quadrant is that in? Quadrant 3, where everything's negative. What about 6, 3? Everything's positive in the first. Where is 0, negative 6? It's not in a quadrant. It's on the y-axis. All right, draw you a little 10 by 10. And let's graph these points and see what we come up with. Let me give you a minute to do that. So what are the points? We had 2, negative 3, is that right? Yes, no, maybe? Okay. And then the next point was negative 2, negative 9. And the next one was 6, 3. I don't really like this either because they're not doing it on the line. I'm going to get me another sheet. All right, and then 0, negative 6. Was that the other one? Okay. And so you're right. If we end up, we notice that it's linear. Now, how would you know if one? Let's say that we got the wrong answer on one of these. Let's say when we were looking back over here. We graphed them, and instead of being over here, it was over here. Would it be obvious to you which one we missed? The one that didn't line up. We missed that. And so graphing it's a good way to check yourself. All right, so hang on just a second. All right, speaking in terms of functions, if an equation is a function, and by the way, you can express a relation 5 different ways, right? Set, table, mapping, graph, equation. If a function, as you said earlier, is a special type of relation, could we not also express a function as a set, table, mapping, graph, equation? If it is a relation, then you can do to a function what you can do to a relation, right? So if an equation is a function, and let's just say, for example, that this equation is a function, it's linear, and it's not vertical. If I know it is a function, then in the place of y, taking the place of y, I can put something in called function notation. And that looks weird, but it's not difficult at all. It's just a type of notation. This says that this equation is a function whose name is f. Usually, why do they say f? Well, function starts with f, doesn't it? They usually use variables f and g and h. Why? I don't know. Why don't we normally use x in an equation? We just do, right? So to name a function, they have f of x in the place of y. And so if I'm graphing, and this is the x-axis instead of the y, this could be the f of x, right? It's just a new name for the y to show that I'm looking at a function, not just any old equation. Does this represent a function? Does each element of the domain pair exactly with one element of the range? Yes, negative 4 is paired to 4, negative 3 is paired to 2, negative 2 is paired to 6, 0 is paired to 4, and 1 is paired to 2. You might say, well, 2x's come to that y. Does the definition say each element of the range occurs one time, or each element of the domain occurs one time? Each element of the domain is paired with exactly one element of the range. So as long as all of these just have one arrow coming out of it, I would draw that definitely down as one of my examples, and underneath that I would say that is a function, okay?
How do you know what to pair them to?
How do you know? Oh, that's given to you. That would be the problem. And see, that's a good question. If I had listed this as a set of ordered pairs, I'd say, well, that's negative 4, 4. That's negative 3, 2. And so you wouldn't have said, where'd that come from? You'd have known it was just a problem. But what do you call this, guys? Yeah, this is a mapping. Let me continue this. I just want to show you something. Negative 2, 6, 0, 4, 1, 2. I said this yesterday. Maybe you've forgotten. To know if a set or a mapping or a table is a function, you look at the x and the x only. And if each of these x's only occur one time, then this is a function. If each of these x's only have one arrow coming out of them, it's a function. It is very simple to tell on sets and tables and mappings if I've got a function or not, because each of those x's just occur one time. So a question, look at this example. I would draw it down too. Is this an example of a function? Does each x have exactly one y? Yes. Now this one y's got 3 x's, but I didn't say that, right? Each of these x's is paired to exactly one y. Each element of this is the domain, and this is the range, just like these were. Domain and range, x's and y's. Each element of the domain is paired with exactly one element of the range, exactly one y. And so this is another example of a function. So sets and tables and graphs are easy. I'll do this one as a table. I've got the x's here, the y's here. 1, 2, 3 are the x's. Each of the y's happens to be a 4, but it doesn't matter about this, the y's. I'm just simply looking at the x's and I'm saying, do each of these x's occur one time, individually, distinctly, just one time? Yes, yes. And so that's an example of a function. All right, now I need you to do this. Look at this set of ordered pairs. This is a set. You agree? This is a set. All right, I need you to express this set of ordered pairs as a table. Ignore the 10, 11, 12, 13, 14, 15, okay? I want you to take this set, express it as a table on your notes, as a graph. You can just do a little 5 by 5 because all these numbers are really small. Do it as a mapping. Express it as a mapping. Give its domain, give its range, and say yes or no if it's a function, and do that right now. Just in your notes, take this set, make it into a little t-table, x and y. Make it into a graph, just a little 5 by 5 is big enough. Make it into a mapping, put your x's here in order, put your y's there in order. Line them up, only list the x's and y's one time in your mapping. Give the domain and the range and tell if it's a function. Right, I'm going to give you time to do that in your notes. There we go. Okay, in our table, we just list our ordered pairs. Now, in our mapping, you only list your x's and y's one time. So in order from least to greatest, so I'd have negative 2, negative 1, 0, 1, 2. And over here you would have 0, 1, and 4. You don't list them more than one time. I know they're used more than one time, but instead of listing them more than one time, you just draw arrows, okay? So for example, negative 2 is paired with 4. Fix this if you missed it. Negative 1 is paired with 1. 0 is paired with 0, 1's also paired with 1, and 2's also paired with 4. That's our mapping. Now looking at this set, do each of these x's occur just one time? Yes. Looking at this table, do each of these x's occur just one time? Yes. Looking at this mapping, does each element of the domain, each of these x's, have only one arrow coming out of them? Yes. So is this a function? Yes. The domain can be, I could find it here, I could find it here, or I could just look up through here. The domain is negative 2, negative 1, 0, 1, and 2. The range is 0, 1, and 4. How did you do? Except for the mapping, probably okay. Now, if I did a graph of that, I would get these points. You can ignore this. Whoops, I don't know if I can get a hold of that or not. But you can ignore this part right here, because actually this is just a set of points. I mean, if I connected them, yes, I'd get a parabola, but that's the set of points, and it is a parabolic shape. Is this a function? Is this a function using the vertical line test? Is this a function using the vertical line test? All right, let's look at this problem right here. Yes, sir.
I have a question on like the table.
Okay, but going back to the table real quick. Yes, sir, right here. On the table, no, you actually just write the ordered pairs across. Okay. All right, let's look at this particular problem. Again, I have a linear equation. It's in standard form, very much like the problem we did a little bit ago. What do they give me right here? X or Y? So that's how I know to plug it in the place of the X. So 2 times 1 is 2. Subtract 2 from both sides. Y is what? 7. And so this point would be 1, 7. Now this would be done the same way, even though this is a fraction. I start to say function again. This is a fraction. I'll put it in the place of the X. And I know we're sometimes a little afraid of those, but hey. What happens to the 2's? Don't they just cancel out? And so, what's Y going to be? And so what's this ordered pair? 5 halves, which is the same thing as 2 1/2, 4. Now when you get down here, you have to be careful, because did they give me X again? They gave me Y. So this would be 2x plus 9 equals 9. Gosh, what's X going to be? Yes. It is going to be 0. So question, where's this point, 0, 9? On the y-axis, on the y-axis. All right, so I'm going to give you a few problems like that to try. Look on page 224. Let's look there together. Get your book out. All right, on page 224, we're going to do 13 through 29. 13 to 29 on the first one, 13 to 17. You give the domain and range, tell if it's a function. 18 to 29. How many equations have you got there? Just one. And you're doing that ordered pair, those ordered pairs are the same one every time. All right, y'all have a great day.